Hi guys, this is the nuclear chemistry short notes. I am going to discuss with you a very important points of nuclear chemistry. Just read these notes and go for your exam. Okay, so you don't need to study anything before your exam. Okay, because you can't study lengthy notes, so that's why I'm making this video. Okay, this is very short notes, so try to make your own notes, okay, within 2 pages. Within 2 pages or within 1.5 page, try to make your own notes. Write down these all points, study these points. These points are more than enough. Okay, just study these points and practice questions regarding nuclear chemistry. That is more than enough. Second thing, so many people are just mailing me and some other people are asking me in comment section to provide my personal notes, right? Still I'm making the videos on every chapter, trying to make videos on every chapter. Still so many people are asking my personal notes. So I just want to clear you one thing, it is very difficult for me to provide my personal notes. First of all, as a brother, as a friend, I just want to tell you one thing. Learn to write your notes on your own. Okay, so just learn this habit. Why? Because without consuming any energy, without making any notes, if you want to crack your competitive examinations, if you want to get your government examinations, it is very difficult for you. In a very friendly way, I'm telling you, please try to understand. One person is asking me to provide analytical chemistry notes. Some other person is asking to provide another notes. How many chapters I can upload? Try to understand this, first of all. Second thing, my handwriting is not clear. My handwriting is very small. That's why the PDF was not clear. That's why I couldn't upload my PDF too, right? So try to understand, and I'm providing lectures here. If you want, please try to make your own notes. That is very important. Okay, so if you take thermodynamics, without consuming any energy, okay, we cannot construct any machine. It is impossible to construct a machine without consuming its energy. So remember that. So when I was preparing for my competitive examinations, I have cleared my masters in 2014. So after 2014, immediately I started my preparation for CSR, NET and GATE. At that time, at least one YouTube channel was not there to guide me regarding CSR, NET and GATE, right? And at least internet facility, proper internet facility was not there. So I struggled a lot. But you have everything now. YouTubers are there, so many YouTubers are there. If you ask anything through mail, every YouTuber will respond, right? So you have so many sources. If you ask anything to make one video, every YouTuber will make the video for you. Still you are struggling, still you are just saying that we can't make notes. This is not acceptable. Please try to understand and try to make your own notes. Okay, right, we will start the class. So the first point, very important point, just make your notes go in a point wise, right? So first point, N by P ratio, N by P equal to 1 to 1.5 if, so if 1 to 1.5 N by P ratio, this is stable nuclei, the nuclei is stable. N by P less than 1 or N by P greater than 1.5, unstable nuclei. This is the first point totally. Next, second point, if N by P less than 1.5, what you have to do? N by P should increase, because whenever N by P less than 1.5, unstable nuclei, so N by P should increase. To increase N by P, what you have to do? Alpha emission or positron emission or electron capture. Okay, among these three you have to do one according to the option. Next, if N by P greater than 1.5, what you have to do? This is also unstable, right? This is also unstable, so N by P should decrease. N by P should decrease. To decrease this N by P, what you have to do? Beta emission or neutron emission. This is the second point. Third point, atomic number greater than 83 and mass number greater than 209, right? If any nuclei you take, if the atomic number of that particular nuclei is greater than 83 and mass number is greater than 209, that nuclei is very unstable, and that nuclei will be called as radioactive nuclei. Next point, alpha. So how you have to calculate number of alpha particles? How many alpha particles will emit in one reaction? How you have to know? Alpha equal to A1 minus A2 by 4. So what is this A1? Mass number. Okay, mass number of first nuclei, mass number of product nuclei. Okay, mass number of reactant nuclei, mass number of product nuclei, A1 minus A2 by 4. Next, the beta particles. Number of beta particles equal to 2 into number of alpha particles minus Z1 minus Z2. That is atomic number of first nuclei atomic number of product nuclei, atomic number of reactant nuclei, atomic number of product nuclei. So 2 into alpha minus of Z1 minus Z2. Next, if n by p less than 1, then how you have to identify when electron capture will be done and when positron emission will be done, right? So here n by p is less than 1. If n by p less than 1 is low, right? If n by p less than 1 is low, that means 0.9, 0.8 like that. If you have the low value, then positron emission will take place, right? If n by p less than 1 is very low, that means 0.2, 0.4 like that, then in that case electron capture will be done, right? So these are the important points. Welcome back. So next one is important properties of alpha, beta and gamma. So the first of all, charge. Okay, charge of alpha particle is +2, charge of beta particle is -1, charge of gamma particle is 0. Next, mass. So mass of alpha particle, there is nothing but mass of proton. So 4 into mass of proton, 1.67 into 10 to the power of 24 grams. So this is the mass of alpha particle. Mass of beta particle, that is nothing but mass of electron, 9.1 into 10 to the power of -28 grams. And mass of gamma particle is also 0. Okay, so charge of gamma particle is 0 and mass of gamma particle is also 0. Next, velocity. So velocity, gamma particle is very high, then beta, then alpha, right? So velocity trend is like this: gamma is greater than beta, beta is greater than alpha. Next, ionizing power. Ionizing power of alpha particles are very high, then beta, then gamma. Okay, ionizing power of alpha is very high, then beta, then gamma. Next, Foreign series. Foreign series means thorium series, right? So here the number is 64. 64 means here number of alpha particles, 6 alpha particles will release, 4 beta particles will release, right? In Foreign series, 6 alpha particles will release, okay, in the conversion of one nuclei to another nuclei, and 4 beta particles will release. In Foreign +1 series, that is Neptunium series, 74. Okay, this is one phone number I have already said you, 64, 74, 86, 74. Foreign +1 Neptunium series, 7 alpha particles will release, 4 beta particles will release. Next one, Foreign +2 series, that is Uranium series, 86. 8 alpha particles will release, 6 beta particles will release. Foreign +3 series, Actinium series, 7 alpha particles will release, 4 beta particles will release in the conversion of unstable nuclei to stable nuclei. Next, binding energy. This is also very important formula, you have to remember and do the questions on this. Energy E equal to delta mc square. Okay, here delta m equal to mass, change of mass. So mass of the reactant minus mass of the product, you have to see, right? Delta mc square. Next one is half-life. Okay, always in nuclear chemistry always follow first order kinetics. Okay, first order reactions and first order kinetics. Here if you see T half, okay, half-life of first order 0.693 by, here lambda we have to use. In nuclear chemistry we have to use lambda, so not K. In place of K, chemical kinetics you already have seen that K. So in place of K we use, in nuclear chemistry we use lambda. Lambda is nothing but decay constant or a disintegration constant. So T half equal to 0.693 by lambda. You have to use this formula. You have to remember this formula. Next, average period, average life period. Okay, average time, T average equal to 1 by lambda. Okay, you have to calculate lambda here and you have to put the value here. T average equal to 1 by lambda. Next one, lambda equal to 2.303 by T log n naught by nt, right? Here in place of a naught by at we have n naught by nt. You have to remember this formula also. How you have to calculate lambda? By using this. You have to calculate lambda 2.303 by T log n naught by nt, and this formula is important, this formula is important, and this formula is also very important. And next one is threshold energy. So before you know about this threshold energy, you have to know Q value. So Q value equal to delta M into 931.5 mega electron volts. Delta M equal to mass of the reactant minus mass of the product in atomic mass units. So Q value delta M into 931.5 mega electron volts. Now if you want to calculate now the threshold energy formula is this. Q value you have to calculate by using this formula, delta M into 931.5 mega electron volts. So you have to put this Q value here, okay, to calculate this threshold energy. So Q value into total mass of reactant by mass of target nuclei. Okay, so we will do the questions on this threshold energy, you don't need to worry, but just remember this formula. Threshold energy equal to Q value into total mass of reactant by mass of target nuclei. Okay, so these are the important and very important formulas and points regarding nuclear chemistry. You don't need to read anything out of this, just remember these points only. Just try to make your own notes by using this video, read them, okay, and practice questions regarding nuclear chemistry. Bas enough for your BARC exam. Okay, so that's all. Thank you so much.